Okay, today is topic 9 and 19, which is electrochemistry. So we're going to talk about definitions of oxidation and reduction. We'll talk about oxidation numbers. We'll talk about balancing half reactions. We will talk about voltaic and electrolytic cells. Then for higher level, we will add cell potential and additional electrolytic cells and delta G. Okay. So the first thing we have to establish are the three definitions of oxidation reduction. And so I think we'll do it this way here. So we'll do oxidation and reduction. So we'll try it this way. Maybe it won't fit this way, but we'll see what we can do. Okay, the first one is in terms of electron transfer. Okay, and oxidation is when you have a loss of electrons. Okay, this is the simplest definition, and then it starts to evolve as we go further and further to be more encapsulated. So when you see this type of reaction, you see a loss of electrons, 3 electrons here, that would be an oxidation reaction. Conversely, a reduction would be a gain of electrons. Something like this, where fluorine becomes fluoride. Okay, and I do want to kind of emphasize this because I don't think we emphasize this enough, but this is the fluorine atom, and this is the fluoride ion. Okay, so the name of the ion changes, the name of the nonmetal changes when it becomes an ion. That's why the naming is the way it is, because really, when you're naming an ionic compound, you name each ion and you just combine the names together. And so, okay, so keep that in mind. The second definition, as we evolve, went into oxygen and hydrogen change. And so here we say gain oxygen or lose hydrogen. So this one tends to be more for organic reactions, like we talked about in topic 10 after topic 9. And so when we're talking about going from an alcohol to an aldehyde or a carboxylic acid or an alcohol to a ketone, we're gaining oxygen bonds and we're losing hydrogen. So this one tends to be kind of more applicable for that. And conversely, the reduction is the loss of oxygen or the gain of hydrogen. The last definition, which is the all-encompassing definition, the one that doesn't have any flaws per se, is our oxidation number definition. Okay, and we'll talk about how to calculate oxidation numbers in a little bit. But so, this one says when you increase oxidation number, there is an oxidation occurring. So when you're going from +1 to +3, that would be an increase in oxidation number. I guess increase implies positive in according to the IB. and a decrease in oxidation number, like from 0 to -2, would be a reduction. So, those are the three different definitions that you need to be familiar with. And I'll add on here about kind of the weaknesses underneath this as well. I probably should do that. And so, we'll do weakness of this definition. So the weakness of this definition under here is that if no electrons are present in overall reaction. So the issue with this definition is if you don't see the electrons in the reaction, you can't tell using that definition. So that's a weakness of that definition. And this is something the IB likes to talk about, kind of a TOK application of this. And so like, why are some definitions not the best definitions? And so if no electrons are present in the overall reaction, then you can't tell which one's oxidizing or which one's reducing. In the oxygen hydrogen, sometimes species can gain oxygen and hydrogen. And so sometimes in these reactions it may appear that it's gaining hydrogen and oxygen. And so it's harder to kind of differentiate between that. I think the kind of most confusing one are combustion reactions, because I think combustion reactions, when you have a hydrocarbon and it breaks up, well, the carbon gains oxygens, and you'd also argue that the oxygens are gaining, I think, what was it? It was for a combustion, it can be confusing because the carbon is, wait, where was that? Am I thinking of combustion right, or am I thinking of a different type of reaction? What was the one I did before? Oh, like a sugar that combusts, that has carbon, hydrogen, oxygen already. It can appear that you're losing oxygens and also, it can appear that you're losing hydrogens and losing oxygens as well. That's what I was thinking about. So like, if you look at C6H12O6, it produces CO2 and H2O. Well, the C actually loses hydrogens and loses oxygens, so it's kind of contradictory. So this definition doesn't always work, but this one does. Oxidation number will always work. And so if you're not sure, then you fall back on that. It can't contradict itself. You'll always have only one oxidation and only one reduction. So one species, one element will oxidize and one element will reduce. I guess also in here I'm thinking about in the weaknesses, a lot of times people can look at the charge and say, oh, this species goes from 0 charge to plus 3 charge, so therefore it must oxidize, but that's not always the case. So if charges aren't present, if you're dealing with all neutral elements and compounds, then you won't see those charges. Like for example, if you look at Mg plus O2 yield MgO, there's no charges to look at, but this is an oxidation reduction reaction because the Mg is going from 0 to +2 and the O is going from 0 to -2. So this is technically a redox reaction, but according to this definition, it isn't. Because you don't see any electrons being transferred, you don't see any charges that tell you. Yes, Anand?
Is that just in the reaction, or can it be written in a way that shows the electrons being changed?
No, I don't believe you can write these synthesis reactions to accomplish that. Questions about that? Okay, so those are the three definitions that you need to be familiar with. Now, the key thing we were talking about before is oxidation number. Okay, And so the oxidation number represents the change in electrons in an atom from its standard state. Okay. So essentially, it's the change in electrons in an atom from its standard state when it's by itself. So this is kind of a theoretical number. It's not always a actual tangible electron transfer. It's just something that's used for keeping track of electrons in an atom. And so key thing here for oxidation state, write number last. Okay, that's something that you don't want to lose a mark for. Okay, so an oxidation state is always written number last. Charge is written with the sign last. And so that's what I always say is like whatever you're talking about, the thing you're talking about goes last. So if you're writing an oxidation number, number goes last. So oxidation number would be represented by like +3. Whereas if it was an ion, its charge would be 3+. And yes, the IB does take a mark off if you write it the wrong way. That's just a silly thing to lose a point for. Yes, Sophia.
What exactly is like the difference between oxidation and
Okay, so it's like an oxidation number kind of states a hypothetical situation when, like, if the two atoms that are bonded together were actually to break apart, who would get the electrons? But in reality, some of these species never end up breaking apart. It's just kind of a theoretical thing. It's like, I guess kind of the weirdest analogy would be like thinking about like a marriage when you're having a joint bank account, right? And so most marriages don't break up, and so it doesn't matter whose money is whose because they're always sharing it, right? But if a divorce happens, then the money gets split. Well, the oxidation number would be keeping track of whose money is who in a marriage, even though it doesn't really matter. But so you could see the change. And a charge would be when the divorce actually happens and the electrons are actually, like the money is actually split. So a charge is a real thing. Like this has happened, bond is broken, this gets 3 electrons, this one loses 3 electrons. But oxidation, we're saying, hypothetically, if it were to happen, what would happen for this? And so this still is important to see what's happening with the change in bond structures of all the species in the reaction, but I think the IB in a lot of books like to call it electronic accounting or electron bookkeeping, because you're keeping track of electrons here, so that if something were to happen, you could see, oh, like in this atom, in this bond, the electron was weaker, the atom was weaker, so it couldn't take ownership of this electron, but in this new bond, it's able to take ownership of that electron because of the difference in electronegativity and pull and things like that. Yeah, Mepsa.
What about oxidation number and charge number?
Oh, well, okay. It's not that they're different, Mepsa. It's just that they don't both exist necessarily at the same time. So, like, what you would say is like MgO, for example. When it's bonded, while there is a charge there, but there's an attraction, but the electrons are still kind of between. Okay, and so you would say the oxidation number is +2 and -2. But when they ionize, when they dissolve in water, then the electrons are actually officially transferred. So now the Mg is a 2+. So this doesn't really have charges, even though like in 10th grade you learn that you're trying to figure out the charges for this. But when it's dissolved in water, then they actually become charged here. So oxidation numbers are always present. Charge is only present when the bonds actually break and the electrons have to make a decision on where they're going to go. So that's the key thing there. So now we have some rules about oxidation number. Okay. let's see. Okay. This might be a little different order than we did before. Elements in standard state are 0. I wrote the slash just because I don't want to confuse anything, but it is symbolized 0 here. So elements in their standard state are 0. Diatomics, metals, whatever, they're 0. Okay. 2. Binary ionic compounds follow most common charges. So do you remember on the periodic table it goes like +1, 1 plus, 2 plus, then jumps across 3 plus, 4 plus or minus, and then 3 minus, 2 minus, and 1 minus. When you're dealing with a binary ionic compound, those are the rules. So you can kind of rely on that. So like if you have something like FeS, well, S we know for sure is 2 minus, so therefore Fe has to be 2 plus. So it'd have an oxidation number +2 and -2 for each of those species. So it just follows the most common charges here. The transition metals are adaptive. Yes?
Is aluminum the only element in its group that removes the electron? Shouldn't all of them be able to do that?
Yeah, they should be all able to lose them, yeah. Zaina, I thought you had a question.
No.
Okay. So, next thing. 3. Fluorine, when bonded, is -1. Always. Okay? So, fluorine when bonded is -1 always. Unless obviously it's F2, but anytime it's bonded to something else, it's always -1 because it has the highest electronegativity. So it will never lose electrons, it will always gain. It will always own whatever electrons that they're sharing with another atom. So fluorine's always -1. 4. Oops, my spelling. Oxygen is -2, except for peroxides, where that is O2 2-, which is -1. And those are very, very specific instances where you don't have a choice. Like it's one of those scenarios where you would want to try to make oxygen 2- or -2, but you can't because it's bonded to something that kind of follows its rules. For example, like let's say you have something like MgO2. Okay, now we know Mg is +2, so by default O has to be -1 in this scenario. So Mg kind of supersedes the oxidation number for O2 here. Or if you see something like Na2O2, that's not a typo. Yes, Chloe.
So like, why does the peroxides like
Well, it's really, you want to think of it like a polyatomic. So what happens is, not to get into too much detail, but you know how oxygens usually double bond with each other? What happens is, in a peroxide, oxygen only single bonds with each other, so it can bond on the other side with other things. So like, for example, hydrogen peroxide actually looks like that. So this is a polyatomic here, and then metals and positive ions can bond on either side of it.
So are they reactive?
Very, very reactive, yes. Like hydrogen peroxide is very reactive and decomposes very quickly into water and oxygen. So very flammable as well. So yeah, peroxides are not very stable. Yes, Madison.
Why can't it bond to the H's when it still has a double
Oh, it's not that it can't, well, because oxygens only tend to have 2 bonds. So, like, it doesn't tend to favor 3 bonds or more. And so it only tends to have 2. So when it's bonded to itself, it has 2, it's already stable. But in different reactions, you can actually make the oxygen break its second bond and bond to hydrogen. It's kind of a very specialized reaction. And these things aren't very stable. Yeah, Zan.
So is like the goal to make it like have like 0 oxidation?
Total, well, that's what we get to next. So the total oxidation state should add up to the overall charge of the species. So, and we're going to get there in a second. Let me write this one more down. 5, hydrogen is +1 except with metals. So you're kind of seeing a pattern here. Metals, like group 1 and group 2 metals, take precedence in their oxidation number over other nonmetals. So like if you see like LiH, Li is always +1, so H in this case has to be -1. And that is known as the hydride ion. The name of hydrogen's negative ion is hydride ion. So this would be called lithium hydride. That's what it would be called. And to kind of repeat what Zaina said, the total oxidation numbers should add up to the overall charge. So whatever the overall charge of the species is, the oxidation numbers should add up to that. This is where we did the chart for the oxidation numbers and things like that, where we organized it. Like, for example, SO4 2-. So 1 and 4. And this is -2 because of our rule before, so that's -8. And that has to equal -2 overall because of this -2. So therefore this has to be +6 and +6. That's one of the rules. That's rule number 4. So oxygen is -2 unless bonded with the metal whose oxidation number is set.
Oh, so,
You could always assume pretty much oxygen is -2.
and it's 4
Because there's 4 of them. So, sorry, to remind y'all, this chart represents number, oxidation number, and total. So the first row is the number of each atom you have, the oxidation number is here, and the total is here. Usually you're trying to solve for one of these oxidation numbers. It's just another way to kind of organize the information. And those are the main rules. I guess, I mean, if you want, we've kind of, oh, question? Okay. I guess if you want, you can also say like group 1 and group 2 metals have fixed oxidation numbers when bonded. They're always +1 and +2 respectively. So that should also be another rule that you kind of want to follow as well. The transition metals can fluctuate, so don't rely on those. Questions about that? Okay. So, how does this help you? Okay. Well, a lot of times the IB will just give you a redox reaction and ask you to identify what's oxidizing and what's reducing. Okay. And so you would see something like I think we were saying before, like CH4 plus O2 yields 2O2 yields CO2 plus 2H2O. And your job is to try to figure out your oxidation numbers according to oxidation numbers. And so here, H is +1. That's what our rule is. We didn't give a rule of carbon. So carbon ends up being -4 here. Oxygen as an element, 0. Okay. Here oxygen is -2, so this is +4. Hydrogen is still +1, and oxygen still is now -2 in both those scenarios. And so carbon is going from -4 to +4. So therefore, it is oxidation. Whereas oxygen is going from 0 to -2, which is reduction. And make sure you're really reading questions carefully, because a lot of times the IB will say, in terms of this definition, or in terms of this, explain why this is oxidation. So if you don't explain it in the terms that they want, then you're not going to get the point. Like sometimes they'll say, explain in terms of oxidation number why this is oxidizing or what's reducing. Or explain in terms of oxygen or hydrogen loss, why is this reduction. So you have to apply it the way they ask you to do it. So really pay attention to the question. Like I said before, IB questions are for the most part, very direct, very concise. And so it's not worth it to kind of skim over them. It's important to read them all. Anon.
This one is in terms of oxidation number?
Yes. So if I asked this in terms of oxidation number, you would say that the carbon is oxidizing and the oxygen is reducing element-wise. But you would say, you got to be careful though, because the thing we haven't talked about is, like, the oxidized species is the whole species. So, like, if I ask for the oxidized species, it would be CH4. If I ask for the element that oxidizes, yeah, you just say C. But the species is a CH4. And the reduced species is O2, which is then our reducing agent and our oxidizing agent. So differentiating between those two and knowing that the agent's the opposite species. So whatever's oxidizing is facilitating the reduction. That's why it's called reducing agent. And the thing that's reduced is the oxidizing agent. Yes, Chloe?
Are there cases when, like, for instance, there's, like, the O2 was reduced, right, to, like,
Yeah.
the oxygen in CO2 and H2O? Are there cases when, like, the oxygen is in the two molecules?
On the products?
Yeah.
Yes, that is the case, and that's why we only talk about it in terms of the reactants. And so, like, when we're talking about oxidizing and reducing, the oxygen could reduce twice into two different substances, but all that matters is the oxygen started this way and that it reduced. It doesn't matter where it ends up in the products.
Can the oxidation numbers be different?
Yes, I mean, that's a whole different story. And so, like, what Chloe's asking is, can an element undergo oxidation and reduction? Yes, it can. Because that's kind of a unique reaction called a disproportionation reaction, where if you look at something like, let's see if I can remember this off the top of my head. So, like, when chlorine gas reacts with water, okay, that's what it produces. It produces hydrochloric acid and hypochlorous acid, HClO. Okay, and so when you look at this, chlorine is 0, and here it's -1, here it's +1. So yes, the chlorine here both reduces and it oxidizes. This is another example of where definitions don't work, right? Because you would argue that this chlorine gains hydrogen in both of these species here. And so it could be contradictory there, okay? But so this is called a disproportionation reaction. I don't think you need to know that term, but it is a possibility that you could have a reaction where one element is both the oxidizer and the reducer based on the products that are produced.
Would that be like a hard exam or something?
I don't think they would ask you that it's a disproportionation reaction, but they could give you that reaction and go, what element's oxidizing, what element's reducing.
You said the same.
You would say the same thing, yeah. And so I guess it'd just be a test, because if students didn't understand that that's possible, then they would try to make up an answer that didn't fit. Questions about that? Okay. Okay. Balancing half reactions. Okay. In acidic solutions. I'm saying that not because you need to know basic solutions, but know that this isn't the only way to do it. If you go into college, you will learn how to balance in basic solutions as well. It's not that much different, to be honest with you. All the first 4 steps are the same. You have to just do one extra step after the whole thing. So, but yeah, the first 4 steps are going to be the same no matter what. Okay. So, 4 steps to balance a half reaction. Okay. What's the first step in balancing a half reaction? What's the first step? Nope. Max?
I can't remember which is first. Add hydrogen.
No. Non-oxygen hydrogens. That's the step that everyone forgets because you don't always use it. But you first balance the non-H's and O's. Okay. By using coefficients. So in this case, that would be Cr2O72 minus yields 2Cr3 plus. Because what you have to remember is that when you balance the reactions, the only thing you're balancing are H's and O's. So anything that isn't balanced before that won't ever be balanced again. So that's kind of what you want to think about it. Well, if I have anything that's not oxygen or hydrogen, then I'm not adding anything else to the reaction, so I can't balance it. So if it's not oxygen or hydrogen, it better be balanced before I continue. Okay? And that's a step that students always forget, like I said, because 90% of the problems you do don't require that step. But the 10% that do are most likely the ones that end up on the IB exam. Okay? So 2, we need to balance O's with what?
Water.
Nope, water. It's okay. That's why we're doing this. Okay? Balance O's with water. Okay? Now, it's the net amount of oxygens. In this case, I only have oxygens on one side, so it's easy. But if you have like 2 oxygens on one side and 5 on the other side, you're only adding 3 waters on one side. Mofe? You have a question?
Yeah, no, it said balance non-H.
No, yeah, 9 hydrogen oxygens.
No, I thought it was like a number, I think.
Oh, okay, yeah, sorry. So in this case, because we only have O's on one side, then we just have to add that number of waters on the other side. But again, count how many oxygens are on both sides and just add the difference to one side. Okay. And what's the next thing we balance? Hydrogens with what? H plus, yeah. Okay, so again, count how many hydrogens are on both sides. Wait, what? Oh. So, balance H's with H pluses. So, this is 14 H pluses plus Cr2O72 minus yields 2 Cr3 plus 7 H2O. So, make sure you're paying attention to your coefficients. Make sure that you're counting how many things are on each side. So 7 H2Os, that means 14 H pluses on this side. And the last step is balance charge with electrons. And this is where students make the biggest mistake. This is where the most common errors occur, because students forget that if you put a coefficient in front of an ion, that also affects the total charge of the ion. So this is 14 plus. Students just start looking at charge and they forget the coefficients. So this is 14 plus here. And this is 2 minus, and this is 6 plus, and this is 0. So the total charge is 12 plus on this side. The total charge is 6 plus.
Mr. Charles,
I'm sorry. Yes?
why do we balance H's with
Okay, because of what we said at the very beginning. These are all acidic reactions. So it's implying that there is some acid in the reaction. So we're going to be using some of that acid for the reaction to occur. So that's why in this case we add H+. In basic solutions, we'll add something to neutralize the H+ on later on out. Zaina. Okay, Tamor.
So when you're about to balance the charges, would you so you have to multiply the right side by 2? Would you multiply the CR or do you multiply the coefficient yeah.
Times the charge.
Okay, no more. I got it.
Zaina.
Okay, when you're doing a problem, and like let's say you put 14 volts instead of, plus 14 in your
Your work?
process, yeah.
No, they're not going to take off for that.
Okay.
So, if you write your signs wrong in there, they're not going to care. Because what they're going to look at is your overall reaction, which you won't ever write those numbers in your overall reaction, so you're okay. So, we have 12 plus and 6 plus. Okay? So, how many electrons do we need to add? 6. On which side? Left. Because we need to reduce this charge down so that it's equal.
How would you do it without so first you'd put 12 on that side and 6 on the left side? How would that
No, well, I think you have backwards on. If you wanted to do it where you're getting them both to 0,
Yeah.
you would add 12 to this side and 6 to this side, which would then be net 6 on this side.
I got it.
If you were thinking it that way, that would work. Okay. So this is net. Okay. Now, if you want to make sure you got your electrons right, okay, if you want to make sure, what I say is look at what is oxidizing and what's the oxidation number that's changing here, okay? And the oxidation number that's changing here is CR. And CR over here is +3. And over here, it is +6. So how much did it change by? 3. And how many times did it change by that? How many times did it change? 2. So therefore, each time you're gaining 3 electrons here, right? But you're gaining it twice. So therefore, you should have 6 electrons. And that's how you check your answer. Right, that's the way to prove that you did it right. A lot of students make mistakes on the electron step. Always a good idea to check that. Go, okay, did my oxidation numbers match the change in electrons I have? If they don't, you did something wrong somewhere. So it's good to kind of check that back. Again, chemistry is all about checking your answer, finding ways to verify or justify your result. Okay? Questions? Yes, Madison.
So, what's the plus 6 one?
That's the oxidation number of CR in this species. I didn't solve for it. It's to figure out the oxidation number of CR here, this is 14 minus, and this is 2 minus, so this has to be 12, which then makes this 6. I'll write it out. So what I was trying to show is 2 and 7 like this. So therefore this is plus 12, so therefore this is plus 6. That's just a work for it. Max?
I have the same.
Okay, perfect. Now, later on this year, we'll talk about getting to know your data packet, because if you realize there's a lot of information in the data packet that reduces what you have to worry about. And this half reaction is actually in your data packet, this exact one, which is great because it's a great way to review how to balance half reactions because it's already balanced for you. So if you look at this half reaction in your data packet, you'll be like, oh, what steps do I need to do? They're all listed out there for you. You have to balance your CRs, then you have to add waters, then you have to add H pluses, then you have to add electrons. And there's really only one way you can do it. So like if you go to the data packet, oops, too far. Here, this reaction, oops, is listed right here. In case you forget how to balance a half reaction, it's all listed there. CR2O72 minus, double that. add waters, add H pluses, add electrons. So it's a good idea to know kind of what's available in your data packet to be able to kind of help balance equations, to kind of reduce the stress about knowing how to do that. Okay. Questions about that? Now, they could conceivably give you an overall reaction and then have you kind of split it up. And so it might be something like, hold on, let me make sure I do, well, I'll just do it this way. So that's 6 electrons. I'm trying to find one that's kind of easy to do. I will just do this. Something like this. Yeah, okay. Something like this. Wait. No, I have it backwards. Sorry. Yeah. Okay, sorry. I have it backwards. So I'm just making up this reaction on the fly, so I want to make sure I did it right. So let's say they give you this net ionic reaction. So just these species that are involved in the redox. If you're going to balance it, you have to split them up into 2 half reactions. Okay? So what are those 2 half reactions going to be in this? Fe3 plus to Fe, and then I minus to IO3 minus. I'm sorry?
I was trying to say something.
Oh, understood. Okay. So then we have to balance them each separately. Okay. Well, Fe3 plus Fe. Well, the Fe's are balanced. No O's, no H's. Just add the electrons. So here we add 3 electrons. Okay. I minus to IO3 minus. Okay. I's are balanced. We add 3 waters. We add 6 H pluses. Now, careful, because this is -1 on this side, and this is -1 plus 6 plus. So that's 5 plus. And this is 1 minus. So how many electrons do we need to add? 6. It's okay. It's okay. A lot of people make that mistake. They forget, like, you're going from negative to positive, so you have to go across the number line. Okay? So, common mistake. That's why I kind of did this. I want to make sure that y'all are kind of avoiding those kind of pitfalls. And so, now that you have your 2 half reactions, how do you combine them? How do you combine the 2 half reactions? Sophia. Oh, sorry. Sabrina. How so? What do you want to cancel out? What's the one thing that's in half reactions that's not in any overall reactions? Electrons. So yes, it is a Hess's law, but all you're having to cancel out is electrons, and then you'll combine the reactions together. So what do we need to do to which reaction? Double the first one, so that we get 6 same electrons. So this is 6 electrons plus 2 Fe3 plus 2 yields 2 Fe. So now the electrons cancel out, and we can add everything else back together. 3H2O plus I minus plus 2 Fe3 plus yields 2 Fe plus IO3 minus plus 6 H plus. Yes, Mefsim. I'm sorry? Oh, the 5 plus is the right side here, because there's 6 H pluses and 1 IO3 minus 1. So that's 5 plus total. Yeah. Any other questions about how I solve this? Huh?
This is so difficult.
It's always easier when you review it. Like, to be honest with you, like, I think it's, yeah, when you see it the second or third time, you already know what to expect, so you're just kind of filling in the gaps, so it always seems a little bit easier. So, but no, it's good that it does appear easier now. We were moving pretty quickly too, I must admit. Okay. All right. The second half of SL is electrochemical cells. Okay. So voltaic cells first. Okay. So it converts chemical energy of a spontaneous exothermic reaction into electrical energy. So we are transferring electrons between one species to another and harnessing that movement of electrons by isolating the two half reactions. So to do that, we have to put two different cells, and one oxidation occurring and one is reduction, and we give only one pathway to travel through to get from one to the other. And that wire is how we harness that electricity. And so our voltaic cell looks like this. And I know something's missing, I'll talk about that in a second. Or later on in this. So these are the main parts that we're going to talk about now for the voltaic cell. So notice we have two half chambers and a wire connecting the different electrodes to each other so that we can collect the electrons as they transfer across. So these are our electrodes. And these are our electrolytic solutions. So these solutions have ions in them which help facilitate this reaction. Now, I'm going to assign my cells here in one way, but it's not necessarily always guaranteed that way, okay? Yes, the conventional method is anode on the right, left, cathode on the right, but don't assume that, okay? Because the IB would find a way to flip it around just to see if students had memorized it versus understanding what's going on. And so we'll call this, for our purposes here, the anode, and we'll call ourselves this the cathode. And the electrons flow from the anode to the cathode. So that's really what you care about here. In a voltaic cell is which way do the electrons flow. Whichever way the electrons flow, it's going from the anode to the cathode. So whichever arrow direction that is pointing to, it's always pointing toward the cathode. That's what you want to remember. Because again, if I were the IB and I knew that most diagrams have the anode on the left, I'd put the anode on the right just to see if students actually understood it or they're just memorizing and regurgitating. Okay, so I'm going to give a reaction here. We'll say Al plus Fe3 plus yields Fe plus Al3 plus. Okay, I don't even know if this is spontaneous or not. I'm just making it up to kind of fulfill this. In HL, we'll talk about whether we can determine it's spontaneous or not. In SL, we'll assume that the reaction they give you is spontaneous. Okay? So, according to this, according to that balanced reaction up there, in the top right corner, which species should go into the anode right here? Okay, why? Huh? I don't know, I'm just asking.
No, it's wrong, I'm wrong.
Why?
Because it's losing
Okay, Al's losing electrons, and what happens at the anode, Zana? Oxidation, right. Okay, so the anode is oxidation. So you should be looking for the species that oxidizes. Al and Al3 plus floating in the solution. So that electrode will be made out of aluminum. And so conversely, you'll have Fe3 plus and Fe here. Because the cathode undergoes reduction. Okay. What's up? One second.
No, it's
Okay. And it kind of makes sense if you think about it, because the electron flow is going from anode to cathode. So the anode is losing electrons, which those electrons are traveling through the wire to go to the other chamber where it's gaining electrons. So it makes sense with the electron flow. Yes?
So what happens when there's no more electrons?
Oh, well, it's not necessarily that there's no more electrons. It's just that, remember, this is the entire circuit. And so what happens is you only get electricity if the flow of electrons this way is greater than the flow of electrons in the reverse direction. When it equals out, it reaches equilibrium and the battery's dead.
But why is it greater than electrons going that way?
Yes.
Why are electrons?
Well, because to complete the circuit, the electrons do have to end up going back this way. Because if you're just going this way, you're not completing an entire circuit. So there has to be a way to kind of continue this motion. So we're missing a piece in here
Oh.
that helps regulate the ions charge. Yeah, the salt bridge. Okay, so Mofe kind of led us to the idea of what we're missing here, which is the salt bridge. Okay. And so the salt bridge is used to regulate the charges of the solution so that the electron flow will continue. Okay. Now, I've added nitrate in these solutions because one, it's makes most salt soluble, and two, it's fairly unreactive, and so it's usually the species that is in there as well. So, what we need to keep in mind is the salt bridge is something like, I don't know, KNO3, like some ionic salt, group 1 salt. In this anode here, okay, which direction are the species moving? In the anode here, which direction are the species moving? Like toward the electrode or out of the electrode? Out. Because it's losing electrons and forming Al3+, like the equation set up there. So it's moving out. So you're making more and more Al3+. Okay? If you're making more and more Al3+, what's the charge of the solution going to become?
Positive.
Positive. Because you're making more Al3+. So it's more positive. Now, that means the problem is if this solution gets too positive, then our electron's going to want to travel all the way across to this species here. No, it's going to make the electrons transfer in here, and your circuit's not going to work. So we have to kind of keep this solution neutrally charged somehow. That's the role of the salt bridge. So if this solution's positive, which part of the salt bridge is going to go toward that solution? Which part of the salt bridge here, KNO3, is going to go this way to neutralize the positive charge in the solution? NO3 minus, exactly. So the NO3 minus travels down here, down the salt bridge here, to attract the Al3 plus out of the solution so it doesn't become positively charged. Now on the right side, which direction are these species moving? into the electrode or onto the electrode this way. So now what you got is what kind of charged solution do you have now that if you're pulling all the positive ions out of the solution? Negative. So therefore this side gets the K plus to attract the excess NO3 minus in your solution. And so ions are moving here, and then electrons are moving here as well. And like Mofe said earlier, like this only happens so much until the potential going over kind of cancels out the potential going backwards, and that's when you have a dead battery. That's when you reach equilibrium. Those two reactions are canceling each other out. So for SL, you're going to be most likely given a full reaction or given the information about a full reaction, and then being able to write it. Just want to make sure. Okay. Questions about the voltaic cell here? Okay. Sorry, does everyone have it written down?
Yeah.
Okay. You just need to see the bottom of some, or leave it here? Electrolytic cells, okay? They do the reverse thing, okay? They convert electrical energy into chemical energy using a non-spontaneous reaction. So essentially, you're putting electrical energy in to force a chemical reaction that wouldn't normally happen. So you're putting in energy into the system to reverse a redox reaction. Oh, sorry, I forgot one more thing on the voltaic cell. I forgot. The voltaic cell has a negative anode and a positive cathode because the electrons are flowing spontaneously toward that. So the electrons are flowing always toward positive, and so in this case, the cathode is positive. In an electrolytic cell, you have just one chamber. Okay. And you have electrodes like we did before, and you have a power source. Whether it's a battery, whether it's an outlet, or whatever, it's just some type of power source. Now you still have your anode and your cathode. Okay. For our purposes here, we'll call this the anode, and we'll call this the cathode. And again, the anode is still oxidation. That doesn't change. The cathode is still reduction. That doesn't change. The electrons still flow from anode to cathode. Okay, so that stuff stays the same. So for both cells, you can say, okay, that's all the same. What's different, though, is that these species that we're dealing with don't want to oxidize and they don't want to reduce. So that's the reason for the power source, because what the power source is doing is overcoming the resistance of those species from oxidizing and reducing. So we are forcing electron flow to happen, which then makes the other species do what they're going to do. And so for anode, we want oxidation. So we want them to lose electrons. So in this case, what charge is the anode going to be to force species to give up their electrons to the anode? Positive. So in this case, it is positive. And the anode, the cathode here is negative. Because the species that in question don't want to reduce and don't want to oxidize. So we have to make the charges of the anode and cathode such that it will force them to reduce and force them to oxidize. So if you want something to lose electrons, the anode has to be positive to attract that and make them lose the electrons to that. Does that make sense? So for SL, in this species, in this solution, will be only molten ionic compounds, okay? Which is good news for you because it keeps things very simple, okay? Now, when I say that, why does it have to be molten?
So it's electrons.
Okay, yeah, free moving ions. Okay, careful with electrons versus ions. In this case, it's ions because it's ionic compound. So you have free moving ions. Electrons usually are explained in like metallic bonding and things like that. So choose your words wisely here. So molten ionic compounds are because you have free moving ions so that electricity can pass through the substance. Okay, if it was solid, it wouldn't because they're all fixed ions. So that's a really important case here. Now, so we'll pick a random molten ionic compound, something like Mg2 plus and Cl minus. Okay. Now, that is MgCl2, and one of these species is going to oxidize, one of these species is going to reduce. Okay. The goal of electrolytic cells is to, for our purposes, create elements, the elements in their standard state. Okay, so Cl minus is going to want to go to what state? Cl2, and Mg2 plus is going to want to go to Mg. So that kind of answers our question for us because if we balance these equations, we'll know which one is doing what. Okay, what does Mg2 plus have to do to become Mg? Gain electrons. Gain 2 electrons. Okay. Cl minus has to do what? Lose electrons. In this case, you have to put a 2 here, so it loses 2 electrons here. So, the Cl minus is going to lose electrons. So it's going to go onto the anode and produce Cl2 gas. Because it is oxidizing. Yeah, that is poisonous. You're right. That's something you should know as well. Okay. The Mg2 plus will produce magnesium metal. Bless you. So, if you were to observe this, you would say Cl2 gas, a yellowish-green gas, would be produced at the anode. Magnesium metal, liquid probably because it's very hot, would be produced at the cathode. And that is the basis kind of this electrolytic cell. Yes, Sophia?
Could you say magnesium would be plated onto the cathode?
Yeah, it's probably liquid, but yeah, you could just say magnesium is being produced at the cathode is fine. I think just to make sure there's no ambiguity there, like that they might try to find a way not to give you a point.
So like builds up.
Yeah, that's fine too. Producer builds up.
So the chlorine is being
Correct, yes. Well, let's be careful there. Mg2 plus is being reduced, Cl minus is oxidized. So be careful. Don't say chlorine and magnesium, because it's really the chloride ion and the magnesium ion. So be careful about that, because those are two different things. So if you're going to say this like Max says in sentences, you're going to say the chloride ion is oxidized and the magnesium ion, is reduced. Yes, Sophia.
Is electroplating something that we can?
That will be in higher level. Okay, that's a good question. That's more of a higher level topic where we'll talk about how much metal we can plate based on current and time and things like that. So, yes, that will be a higher level thing. Yes, Chloe.
What's the magnesium that's produced? Would it be like reactive?
I guess theoretically, if it's exposed to air and things like that, it could kind of oxidize based on the heat and stuff like that. But I think in this case, I'm not sure how the conditions are set to just prevent the magnesium. I think the magnesium is probably going to be built at the bottom within the molten. Like it's not going to be exposed to air. If it's exposed to air, then it's probably going to oxidize. So it'll probably be plated around like the bottom of the cathode. Okay. Questions about that? Okay. One last thing, we kind of go back, and we'll be done for S cell. Okay, and that is biological oxygen demand. Okay, or BOD. Biological oxygen demand is a real-world application of oxidation reduction reactions. That's really the only purpose of it for incorporating the IB. They're trying to show environmental connections to chemistry. And so biological oxygen demand is a redox reaction that they use to measure how much organic material is in, how much organic waste is in the water. So they're trying to tie it into saying, well, it is technically a redox reaction the way we test it, so we're going to put it into topic 9. And so biological oxygen demand measures the biological waste in water using a redox reaction. And you don't have to memorize all the reactions. This is called the Winkler method. I think they might reference it, but they're never going to ask you to cite the Winkler method. So it's a titration, it's a bunch of reactions. You're not going to memorize the reactions. Really what you want to focus on is the fact that we realize that 4 moles of S2O3 2- reacts with 1 mole O2 in this whole process. So that's the multiple ratio you really care about, because the IB will give you the volume and the molarity of the thiosulfate that you use, and you can work your way backwards to get the molarity of oxygen. So you'll know the sample. So really it's the molarity of the S2O3 2- times the volume of the S2O3 2- times the molarity of O2 and then the volume of the water sample. They don't say the volume of O2, they just say the volume of the water sample, which is the same thing. So what you're really solving for is this, the molarity of O2. So what does a molarity of O2 mean? We need to convert that to parts per million. That's the big kind of conversion here. So when you get the molarity here, like let's say it's 0.00245 moles of O2 per 1 decimeter cubed. So like let's say we solve for that. Now what we need to know is that parts per million is equal to milligrams per decimeter cubed. So this is our conversion. So we have to convert moles of O2 to milligrams of O2. Okay? And so the first thing we have to do is convert moles to what? Grams, which is 32 grams of O2. And then we have to convert 1 gram of O2 to 1,000 milligrams of O2. And that answer here is my parts per million. And that's my biological, that's the O2 left in the water. So the Winkler method measures how much O2 is left after 5 days to know how much was used up. So what you do is then you calculate the pure water minus the O2 left to get the biological oxygen demand. Yes, Sophia?
Is that like pure water and?
At that temperature. So, sorry, yeah, so at that temperature, how much O2 is in pure water? Yeah, so that's like completely pure water.
They give you that?
Yes, they have to give that to you.
What are the units?
Parts per million.
Okay.
It is ppm. So they'll tell it to you in ppm.
Parts per million for pure water?
Yes, so it's parts of O2 per million parts of water. And obviously you want the BOD to be as little as possible, because the larger this number is, the more pollution is in your water. Okay. This kind of concept is the same we do for all redox titrations. It's just that the mole-to-mole ratio changes. So you have to know how to calculate redox titrations. You do a redox titration just like you do an acid-base titration. There's really no difference. You have molarity and volume, unknown molarity and volume. You have a balanced equation. You solve for it the same way, whichever way you want to solve for it. So this is also useful as a concept for just any redox titration. It's just our mole-to-mole ratio changes. Questions about that? Okay. That's the end of SL.